have the last lecture with me, where we are going to talk about deploying machine learning in production. So just a bit of motivation before we start here. So it's a growing need for machine learning products and services. So machine learning is already having a huge impact on us. So due to rapid advances in machine learning fields like computer vision, natural language processing, recommendation systems, and so on. So data science and machine learning are becoming core capabilities for solving complex real-world problems. So as we have seen earlier in the lectures, businesses are investing in their data science teams to develop predictive models that can deliver business values for their customers. So we have looked at this machine learning system workflow before as well, or all the components. So it consists of several components, as we can see from this paper called Hidden Technical Depth in Machine Learning by Scully et al. So the machine learning model is just a tiny fraction of an overall system. So the required surrounding infrastructure is vast and complex. However, you have insight into some of these or many of these components through your bachelor studies. So here's a more complete workflow that we saw in the last lecture. So yeah, starting with understanding the problem, then looking at the data and doing feature engineering, then modeling, then the deployment part. So as we discussed at the end of the last lecture, this is potentially the most challenging stage. So today we will start with looking at this component called deploy. So model deployment is the process for making machine learning models available in production environments where they can provide predictions to end users or other systems. So the full value of machine learning models comes from enabling others to use them. We cannot just assume that people know how to use Jupyter notebooks. So how is this process? So you start off with training a model first. Then you make your model available to end users through providing an app or a service for interaction. So managing deployed systems is quite a challenge as it requires making changes. So this could be while the system continues to serve the end user. So therefore, it is important to update your model, and we will discuss about this later in this lecture. So yeah, machine learning, deploy machine learning systems have a couple of challenges. So it involves challenges of traditional software programming, like reliability. So that you produce the intended results and be robust. So testing is important here, and reusability. So reuse the system or part of it. And maintainability is to maintain the software, and flexibility is that you can easily add or remove functions. So then in addition, you have machine learning specific challenges like reproducibility, data drift. So yeah, we will talk about this also later in this lecture. So as you probably have seen now while you've been working with your project, is that models become complex in an effort to find ways to increase your accuracy. So the natural impulse is to imply more and more complex model architecture, and this could also include more and more features. So this often results in longer prediction latency, but hopefully boosts in prediction accuracy. So as the complexity increases, the resource requirements increases for each part of the training and serving infrastructure, which means that it is also an increase in cost. So this could be in a form of hardware requirements like GPU, CPU, and higher support and maintenance burden for software engineers, and many more other things. So the challenge for machine learning practitioners is to balance this complexity and cost. And how can we find the balance between complexity and cost? So that depends on the use case. So you need to decide based on two matrices. So optimizing matrices, it reflects the model's predictive efficiency, like accuracy, precision, recall, and many more other matrices. So it gives a good values in these matrices is a strong signal about the quality of your model. So the other one is satisfying matrices. So it reflects an operation constraint that the model has to satisfy, like latency, model size, and so on. So you can, for example, set a latency threshold to a particular value, such as 2 seconds, and any model that doesn't meet this threshold is not going to be accepted. So here's an approach for how we can do it. So you start with specifying your infrastructure. So if you want to put your model on a server or on embedded devices, so here you have to think about the GPU, CPU, storage, and so on. On embedded services, the computing power could be less than on a server. So, but in some cases, it's critical to take actions based on predictions made in real time. And in those cases, it would make natural to have those kind of applications on embedded devices, like for autonomous vehicles. But for like recommendation systems, prediction latency might not be super important. So as we can see here. So when we have decided this, the next step would be to train your model and improve the predictive power. And you repeat this until you hit one or more of your metrics on the infrastructure. So after this, you assess the results. So you accept it or make the decision to increase the specification of the serving infrastructure. And then you go back and do this process again. Okay, so let's say that you have accepted your model. So then you have two main types of predictions your model can do in production, as we have seen in this Streamlit tutorial I put out some weeks ago. So the first one is batch prediction. So you make prediction on a batch of observations. And this is often made using old data. So like you have an CSV file that you can send it. So another approach is online prediction. So predictions are generated in real time upon request on a single observation of data at runtime. So here are some important metrics for optimizing machine learning inferences. So you have to look into latency, throughput, and with these, it also comes to cost. So latency is the delay between users' action and response of applications to users' action. So minimal latency is often a key requirement to maintain customer satisfaction, especially in online inference. Then you have throughput. So that's the number of successful requests served in a unit of time. So for instance, in seconds. And in some applications, only throughput is important and not latency. For example, in high traffic web services, you can take requests from multiple users for some specific tasks. Okay, so making latency and throughput as efficient as possible will come at a cost. So this would be in form of infrastructure and also in engineering and testing time and software license and many more other things. So the cost associated with each inference should be minimized within the relevant constraints. Okay, I will take questions at the end. So additional optimization areas you can focus on is pre-processing and post-processing, as you have seen in your assignments you have been working with. So data pre-processing is that the data being passed into the system may not be in the same format as the model was designed to take in. So this could, for example, be converting dates. As you can see here, you start off with some string dates, then you convert it into features to get more information. Okay, so you have some pre-processing operations needed before you do inference. So like data cleansing, so correcting invalid values in incoming data and feature tuning, normalization, scaling, clipping outliers, imputing. So if what you're going to do with the non-values and so on, then you have feature construction, combine inputs or feature crossing, where you combine features, or so the next is representation transformation. So change data formats for the model. So this could be one hot encoding or ordinal encoder. Then you have feature selection. So you apply same feature selection done on training on incoming data. So instead of going through cleansing, tuning, construction, and representation transformation, you could just have the input data format pre-transformed to cache. And you can do this with scikit-learn pipeline, or this is also what happens in PyCaret when you write model.save, then load the model. Okay, so then you have some post-processing stages, which is usually in everything in pre-processing, but in reverse. So for example, converting the predictions from binary value to string, as we saw in the tutorial for Streamlit, or you can also thresholding or binning the predictions. And this can be very application specific. Okay, so now we have looked at this deployment part. So let's say that we put our model into production. So the next thing you have to do then is to monitor and update your model. So model monitoring and logging. So without this, you are unlikely to be aware of the problem. So why monitoring? So it provides early warning of things that can be gone wrong while a machine learning model is in production. And there are multiple reasons why this can happen. So you have data squeeze. So occurs when training data is not representative of the live data. For example, a feature is not available in production environment. Then you have model staleness. So the collected data might not longer reflect the current state. So for example, change in customer behavior. Then you also have something called feedback loops. So this arises when you automatically train your model on data collected in production. So if the data is biased or corrupted, this may change the behavior of the machine learning system. So monitoring in machine learning systems can be divided into two parts. So you have functional monitoring. So there you look at the predictive performance. This could be through in an unsupervised way. So you compare your model's prediction distributions, and when you have the labels, you can look at the labels. And yeah, also changes in serving data, metrics is used during training, and characteristics of features. And then you have non-functional monitoring like system performance, system status, reliability, resource utilizations, and other things. So, okay, so collecting all the context information is often not practical as the amount of data to process and store could be very large. But it's important to collect some of these. So one of the key problems in many domains is model decay. So production machine learning models often operate in dynamic environments. So the ground truth in dynamic environments might change over time. So if the model is static and does not change, then it gradually moves farther away from the ground truth. So this is mostly caused by data drift, concept drift, or both of them. So what is this? So let's look at what data drift is, also known as feature drift. Changes like this often occurs in demographic features. So it's statistical distributions of production data from training data. So it is changes in the real world. So trained model is not relevant for the changed data, and therefore the model accuracy suffers. So as I said, it is often occurs in demographic features like gender and age, which may change over time. So here's just an illustration of monthly active users on Facebook in 2004, where more younger people are active compared to now. So that's an example. Then you have concept drift, which is the relationship between features and label changes over time. So the meaning of what you're trying to predict changes. So when the pandemic hit us, toilet paper sales suddenly raised. So that's one example. Then another example could be, for example, Twitter, when they started, they hadn't that much of, or in the beginning, there were not that many users compared to today. So the tweets in the beginning could be less often sent out, while now it's more often. So that could, if that would have happened at that time, that could have been seen as spam, for example. So you have to change the data. So way to mitigate these problems. So you have to monitor your data through logging, since this provides valuable insights, and it can also focus on specific events, which can be used to investigate incidents and help with root cause analysis. So it is also easy to generate this. So when you have detected model decay, you need to let others know about it and take steps to bring your model back to an acceptable performance. And you can do this by either fine-tuning it or start over. So you can, from the last checkpoint using new data. So the important thing here is that you have to have version control on your models and data, and not only the code. So if you think about starting over and retrain your model, then you should consider redesigning your entire pipeline. And also think about the feature engineering and feature selection, and investigate on alternative architectures that are out there. So which approach you want to use depends on your model performance. So how much new label data you have. So if you have enough data, then you can just throw away the old data and train on the new data. And also look at how far the data has drifted. So the point here is that no model lives forever. So periodically, you need to go back to the drawing board and start over, applying what you have learned since the last time you updated your model. So that's it about machine learning in production. So tomorrow we are so lucky that we are going to have a guest lecture with Bouvet, so the head of the data science department will talk about their experience from a data science project. So in next week, I will prepare some machine learning sample questions. So that will be multiple choice and some written. And yeah, I will come back to that. So next week, on Thursday, we are so lucky that we will also have another guest lecture with Alexander Lundevold from Moon Medical Imaging Visualization and Imaging Center. So yeah, with that, I will stop the recording. Then I will take questions.